Okay, and for the final talk today, it's my pleasure to introduce Hong Seo, who has been working at the Massachusetts Institute of Technology in plasma physics under a name that a lot of us know, Richard Petrasso. Hong has done his practicum location in 2014 at Lawrence Livermore National Laboratory, and today he's going to be talking about time-resolved nuclear diagnostics for probing implosion dynamics and kinetic multi-ion effects on omega and NIF, so follows on nicely from the talk this morning. So, Hong, it's yours.
Good afternoon, everyone. So today I'm going to talk about time-resolved nuclear diagnostic and using it to understand ICF implosions on omega and the NIF. So this is just a very quick snippet where this is a cartoon schematic diagram of a diagnostic that we'll talk about, the particle X-ray temporal diagnostic, and the X-ray and neutron emission history measured with this instrument. And so this is actually a two-part talk because I have two different diagnostic and physics projects on omega and the NIF, so I will try my best to do both justice. On omega, we're interested in understanding kinetic and multi-ion fluid effects in ICF implosion and assessing their impact using nuclear reaction and the core X-ray continuum. And to do this, we have designed and implemented a new diagnostic called the particle X-ray temporal diagnostic. And on the NIF, we're interested in understanding better implosion dynamics from measuring the shock and the compression bang times. And this is done through the new magnetic particle time of flights magPTOF diagnostic, one of the 50, 60 or so diagnostic that John talked about this morning. And so lots of collaborators for the Omega projects from MIT and several national labs. Lots of collaborators on the NIF projects from MIT and several national labs. All right, so let's get some standard context on ICF first. So the goal is to really compress the fusion field to high density and temperature and then contain it by its own inertia long enough for you to get ignition and burn. So you start off with a capsule that's about 2 millimeters and you use X-ray or laser drive to irradiate it and heats the surface, and that increases the pressure. And that ablation of material on the outside pushes the rest of the material inwards, so very much like a spherical rocket continuing on the rocket beam. And this compression increases the density and the temperature of the field, which is what we want. You're converting kinetic energy into potential energy. And finally, you reach the last stage, what we call stagnation, where you have assembled a hot spot and surrounding it a layer of cold DT ice field. And the goal is to have the fusion alphas from the hotspot depositing its energy in the cold DT ice, burning that, and then setting off a hopefully propagating burn wave. And so the tone that I want to start off today's talk with, and I think the tone that ended with John's talk this morning, is that ICF implosions are really, really hard, and we don't understand a lot of the physics. And so with that in mind, we're going to go now into omega and look at some of the physics studies that we are doing there with this in mind. So a very quick primer, omega is a very versatile ICF facility that is for looking at implosion and high energy density system. It is a 60 beam laser symmetric drive. You get about 30 kilojoules over about nanoseconds, and you get about 12 shots per day. It is a very mature user facility, and I heard it described as an excellent data factory, which I think is really the highest compliment that you can give to a user facility. And so this is really nice because you have enough shots per day that you can really carry out an entire physics campaigns in 12 shots and scan the parameter space that you need. So on to the physics that we're going after. So during the shock propagation phase of an ICF implosion, the ion-ion mean free path, or lambda II, in the field is in the order of the implosion radius because of the very high temperatures and low density. In particular, if you look at this radius versus time diagram, so you have your ablator outside, you have your DT ice, and then you have a DT vapor. what you're looking at is the trajectory as the implosions implodes. In particular, if you look at the shock, this innermost line coming into the gas, you're sending a very strong shock through a very low density gas, heating it to high temperature and low density, and that resulted in a very long lambda II in the field during this shock phase. What's the problem with that? So some definition that we'll use throughout this talk, kinetic physics refers to phenomena that happens at time or length scale that are of the particle collisions. So in our case, the collision time scale, length scale we are interested in is the lambda II. And hydrocodes assume that these collision length scale, lambda II, are much smaller than the scale of interest. That is, in this case, the radius of the capsule. And so this condition is generally not true at all during the shock phase. So you can see here the radius is probably about 200 microns and the lambda II is on the order of 100-ish. So that is very much not a hydrodynamic conditions. And so kinetic effects refers to observed phenomena that results from these kinetic physics that are not captured in hydrocodes. We want to study these kinetic physics and assess its impact on ICF implosions. And so we want to look at the impacts of kinetic effects in the shock phase of the most complicated ICF targets there is, cryogenic targets. And that's really hard, and we don't want to do that because no one wants to deal with cryogenic targets unless they have to. And even then, it has tritium in it, which makes everything messy. And so to get around that, what we're doing to study the shock phase is to use the simplest possible ICF targets. And that is just a thin glass shell filled with D-helium-3. It turns out that if you hit it very hard with a strong laser pulse, you actually get very similar shock and lambda II conditions in these purely shock-driven thin shell implosions. And in this sense, these thin shell implosions that we study on omega are excellent surrogates for understanding the shock phase and kinetic effects in much more complicated ICF implosions on the NIF. And so using these exploding pusher platform, time average quantities, by which I mean yields and ion temperature, have been used to look at the implosions as they transition from a more kinetic-like to a more hydrodynamic regime. So here is one example of the study where, the initial gas fill of the target is varied, and you're looking at the measured nuclear yields. And so at very high density gas fill, where you're in a much more hydrodynamic regime and the ion-ion mean free path is much shorter, you see that there's actually pretty good agreement between simulated yields and measured yields. And on the opposite side, when you have very low initial gas fill, so that your ion-ion mean free path is very long, you see an enormous disagreement between the measured yields and the predicted yield. So what we call the yield over clean, or just the experiments over the 1D yields, is actually about 3% in this very low case. So that tells us that there are very important physics that are not being adequately captured by the 1D hydrocodes in this kinetic regime. But again, these are all using time-integrated quantities. And so the goal of the particle X-ray temporal diagnostic is to understand the impact of kinetic effects in ICF implosions using time-resolved data. And that gives you an extra dimension of information to fetch out these subtleties. And if you want to kind of get a visual feeling of what are the effects of these, what is the actual effects of these non-hydro codes, non-hydro effects, what we have here is a multi-ion fluid simulation of an ICF implosion using a PIC code that shows species separation and thermal decoupling of a DT plasma during shock, rebound, and convergence. What I mean is that for this ICF implosion here, you're looking at the density and temperature profile as the shock propagates inward, so toward the left-hand side. And what you see is that as the shock propagates inward more and more, you see separation between the deuterium ions and the tritium ions in space, and you also see a difference in their temperature profiles. So, this is all very philosophically interesting and good thing to think about on top of a mountain. But as an experimentalist, what I'm thinking is, what does this mean? And does it turn into something that I can measure and quantify? And the answer is probably. So taking all of those profiles that you saw in the previous slides and converting it into a reaction history, so nuclear yields produced it per time units. This is the burn history that you see for the DD and the DD reaction for these implosions. And when you go to a 2-ion fluid simulations, what you see is that there are quantitative changes in the reaction history that can be measured. And in particular, we're talking about quantitative changes in the ratio of the yields as you transition from average ion fluid to 2-ion fluid. We're talking about timing shift in the burn onset between the reactions as you go from 1 fluid to 2 fluid. And we're also talking about changes in the relative bang time or peak thermonuclear production time for these implosions. So these are the kind of quantitative effects that we would like to investigate, and that will tell us, or at least give us a hint of the impact that kinetic effects may have on these implosions. And the time scale of these effects that we're looking at is on the order of 30 to 50 picoseconds. And that really sets the time scale of the precision that we need our diagnostic to have in order to capture and quantify these effects. And catapulting off what Marina said this morning, a negative result is just as important as a positive result. In that, if we found out that kinetic effects have 0 impact whatsoever on ICF implosion, that is fantastic. We can now spend our time doing something useful. But if it does have an understandable and measured impact, then it is time to consider seriously mitigation strategies. So enough motivations. Let's talk about the diagnostic now. The particle X-ray temporal diagnostic is a multi-channel streak emission history diagnostic that is sensitive to charged particles, neutrons, and X-rays. So here in this blown up portion in the center, you have the implosions. And 9 centimeters away, you have a nose cone with different scintillators that's filtered for neutrons or protons. And as charged particles, X-ray and neutrons hits the scintillator, it deposits energy and you get scintillator lights. These lights are relayed outside to the target chamber through a 3.5 meters optical relay. And when you actually look at the data that this diagnostic produced, that's what it looks like. This is a streak image, and the horizontal axis is the time axis. And on top, what you're seeing is the omega fiducial cone for absolute timing. So using this configuration, what we did is on the top half of the trace, we measured the 2.45 DD-neutron history coming in from the implosions. And on the bottom, we are measuring the 14.7 MeV D-helium-3 proton reaction history coming in from the bottom. And we have diagnostic that can measure proton reaction history. We have diagnostic that can measure neutron reaction history. And the innovation and what we're really striving at is that we're doing these measurements on the same diagnostic. And because of that, we can get rid of all cross-timing uncertainty and jitters, and we can achieve a timing precision on the order of 15 picoseconds or so, which we think is what we need to really differentiate between these plasma effects that we discussed earlier on. So what's better than 2 different streak channels that you can filter to look at whatever you want? It is 3 different streak channels that you can filter to look at whatever you want. And that is what we did. In this slightly upgraded configuration, we have 3 individual streak channels, and this particular example is looking at the X-ray emission histories from 3 different X-ray bands from an ICF implosions. So it's looking at the X-ray greater than 6 keV, greater than 12 keV, and greater than 20 keV. And what's remarkable about this data is that for an electron temperature of about 3 keV, you expect about 3 orders of magnitude difference in these 3 signals. And so the reason why we're able to get everything nicely behave and on the same streak image at the same magnitude is that we have individual filterings to adjust them accordingly. So we talked about nuclear reaction history, we talked about X-ray emission histories. And so our ultimate goal for this diagnostic is to really combine all of those measurements and measure them all at once, because why not? This is one particular example where I'm showing the nuclear emission history and the X-ray emission histories on the same data streak. And because everything is done on the same diagnostic, you get very good relative timing between the nuclear and the X-ray information on the order of 10 picoseconds. And so that is really what we're hoping to do with this diagnostic, is to use precision measurement of X-ray and nuclear information and their time differences to look at kinetic and multi-ion fluid effects during the shock phase of ICF implosions. And we can do this because these measurements are highly precise relative to each other. And so Los Alamos group is helping us out with the kinetic and multi-ion simulations using LSP, and we are getting more data from this project in August. So I can and have talked about this project for another hour, but in the interest of time, I'm going to move on to the NIF world, and don't worry, this is the shorter part of the presentations. So on the NIF, we're interested in looking at implosion dynamics from measurements of shock and compression bang time. And to do this, we have implemented an improved diagnostic we call the magnetic particle time of flight diagnostic, for which I'm the responsible scientist on the NIF. And being a responsible scientist on the NIF just means that everyone asks you to analyze stuff. It doesn't actually come with monetary compensation. One slide primer on the NIF, the National Ignition Facility is simply put the most energetic facility in the world. So in comparison to Omega, we now have 192 beams, and you have about 1.8 megajoules over about 20 nanoseconds, and you have about 2 to 3 shots per day. And now it actually turns out that while a lot of the integrated experiments, ignition experiments on the NIF use a DT fuel, surrogate implosions filled with D-helium-3 are actually used to study a lot of the basic implosion physics. And this really comes back to the fact that no one wants to deal with cryogenic targets unless they have to. And so you want to use the simplest targets that will still allow you to study the physics that you want, because that way they are easier to feel, so you can have more of them. And so instead of this relatively complicated target, instead the surrogate implosion that we'll focus a lot on is just have a simple ablator filled with a D-helium-3 gas. And because of D-helium-3 gas, we also have these standard charge and neutron particles that allow us to make a lot of novel diagnostic measurements. For example, you can actually use these nuclear fusion products to study confinement and burn properties. And this is done by using the D-helium-3 protons from the implosion, which is 14.7 MeV. As the proton escape, it loses energy based on how much stuff it sees on its way to the detector. So over here, where it says shock rho r, this is the protons that escape during shock time. And you know that because it is higher energy, so it sees less stuff as it escapes. These protons that are lower energy escape during compression. And that's because it has less energy because it sees more stuff by the time it escapes. And these measurements are done using the MIT wedge range filter proton spectrometer that we use to measure the evolution of areal density, which is a very important confinement metric from shock to compression. This effort is led by Brendan Lohman, a current MIT graduate student, and former SSG and current SSGF alumni, Alex Stilstra, who did his practicum in Livermore, but is now a Reynolds postdoc at Los Alamos. So we'll come back to these proton spectrum and ρr measurements later. But now let's focus and talk about timing. In ICF implosions, nuclear burn occurs at 2 different times, the shock burn and then a compression burn. If I can get that to, okay. So here is your usual RT diagram, and as the shock, which is the red line, comes in and hits the center and rebound, that initial spike in temperature gives you your first burst of thermonuclear fusion productions. And that area, that time, we call the shock bang time. And as your implosion fully compresses and reaches the highest convergence, so it stagnates, then that increased density and temperature gives you the second burst of thermonuclear fusion, what we call the compression bang time. The MIT magnetic particle time of flight, or magPTOF diagnostic that I am responsible for, measures both the shock and the compression bang time on the same diagnostic. And it is in fact the only diagnostic on NIF that measures the shock bang time, which is an important metric for quantifying implosion performance. Talking about pTOF a little bit first, the particle time of flight, which is the magPTOF without the magnet parts, is a nuclear bang time detector that's sensitive to X-ray protons and neutrons. This is a very simple detector. It's very small and it's just mounted on the 9078 diagnostic insertion manipulator. And what it is it is a CVD diamond that's biased at high voltage. And when ionizing radiation hits it, it bumps electron into the conduction band, and these charges are swept out by the bias, and what you get is a current impulse on your scope. And so pTOF has been a reliable nuclear diagnostic for shots with low X-ray background on the NIF for many years now. The magnetic part comes from we need to cut down the X-ray signal on magPTOF so it can measure protons reliably. And to do this, this is the trusty pTOF detector that we see before, and now we have a much bigger X-ray filter in front. And to get the protons to the detector, we added a permanent magnet that bends the protons around the X-ray filter and into the pTOF detectors. And so this is what the detector actually looks like with pTOF in the back, and this is the magnets housing here. I would say this is the quintessential picture to keep in mind when thinking about what magPTOF is supposed to do. You have very low X-ray signal, which is good, and you're measuring the shock protons that comes from the implosions and the DD-neutrons that come from the implosions, both of which give you timing information. Going back to the RT diagram, at shock time, you're seeing the D-helium-3 protons that escape, and at compression time, the DD-neutrons give you the compression bang time informations. And now we can all put it together and discover something kind of cool about these implosions. And that is, we already talked about the magPTOF data. That is, you have the shock bang time and the compression bang time. And we also talk about the proton spectrum measured by WRF, which gives you the shock areal density and the compression areal density. And now we can combine both of these diagnostic and their information, because now not only do we know what the shock and the compression ρr is, we also know at what time that is. And so we can put the ρr on an absolute time scale, which is what we have done here. So here we have plotted the rho r as a function of implosion time, and the gray bar here denotes the measurements uncertainty. And the advantage of that is now we are really in a position to constrain the evolution history of areal density as predicted by simulations, because we have explicitly measured the areal density at 2 well-defined time. And this is information that we can directly compare to simulations and to see whether it matches their expectation. And it's one additional piece of goodies that help us understand what the implosion is doing. And this is definitely one example where when you put information from multiple diagnostics together, it gives you new insights that you would not have otherwise. And so a lot of this is really possible because we're able to develop our diagnostic at MIT at our accelerator facilities. And so we are able to test, calibrate, and just test new design at our accelerator. And that's very important before fielding these diagnostics at NIF, Omega, and Z. And these are pictures of graduate students and undergraduate students posing for photos. And so in conclusion, my graduate work has focused on using time-resolved nuclear diagnostic to better understand ICF implosions on Omega and the NIF. On Omega, this led to the implementation of the particle X-ray temporal diagnostic, from which we hope to use to assess the impact of kinetic physics on ICF implosions. And on the NIF, the implementation of the magnetic particle time of flight diagnostic allow us for the first time to robustly measure shock bang time in D-helium-3 surrogate implosions on the NIF, and also compare the timing difference between the shock and compression bang time. So this is my graduating year, so a few final remarks on the fellowship. And that is for someone who appreciates knowing a lot of breadth, even while burrowing into my depth, that breadth provided by SSGF has been extremely valuable. And as we all know, and I know would agree, this is a very well-run and extremely friendly fellowship, and it's really been an honor to be part of it for 4 years. Thank you.